Welcome to the first video for remote learning. I'll be your host, Mr. Pata, and today we're going to be picking up right where we left off at the end of the last week, where we're talking about this idea of what I like to call the motion quantity. We were looking at it in terms of the collisions or explosions between two carts, and we were linking it to the idea that if you could understand the energy, then you could understand the motion quantity and how these two things are related. So let's pick up with one that I think we talked about, but I think will be very instructive. And it's this one where you have a cart and it's moving in here, okay? And then there's another cart here, and this one's got some mass on it. And this one's stationary. So this is the before situation. Then the after situation looks like this, where the first cart hits the second cart and it sticks to it because the magnets that are there. And the inherent question here is, how does the total energy here compare to the total energy here? And how does the total motion quantity here compare to the total motion quantity there? So let's put some colors on these bad boys. So we're going to say that they're two individual objects to start, and then they're one combined object after. So we'll make this one red. Make this one green. And we'll say that this whole thing is blue. What the colors do is they enable us to look at the diagrams with a little bit more precision. So what does this look like? Well, one of the things we know about this is we can analyze the energy before and after. So we know we're talking about gravitational, kinetic, and elastic. Talk about gravitational, kinetic, and elastic. And let's analyze the system. Where there's a system. So in the system, we're going to have cart red, and then cart green. And we know that together they make this blue cart over here, so we don't need to include it. So this is all right. So when I look at this, one of the things that I know is that the red car is moving before and the green car is not. So the red car is going to have some energy. Now, what we're going to do is we're going to draw the energy on here. We're going to use our 4-bar situation. But I don't actually know how much energy there is. We're going to put some masses and some speeds on here in a second to make it more quantitative. But when I come over here, does it have the 4 bars? Does it have less? Did we lose some to the surroundings? I don't know. We're going to have to analyze the motion first, and once we analyze the motion, then we can go back and analyze the energy. So let's look at our motion chart again. So, in essence, this motion chart down here is a bar graph, but instead of the bars being vertical, like the energy bar graphs, our bars here are horizontal. So, let's put some masses on these bad boys so we can see what's happening. So we're going to say that our cart is 0.5 kilograms, and it's moving to the right, and I'm just going to make up a number, and we're going to go with it. Let's say it's moving to the right at 6 meters per second. Now, it can't really go 6 meters per second, that's like 12 miles per hour, but for the sake of being able to make the numbers look nice, let's do that. We're going to say this one is twice, so this is a total mass of 1 kilogram. It's twice as much as that one, and right here it's 0 meters per second. So what about the blue one? Well, if it's the carts combined, it'll be 1.5 kilograms, and the question is, basically, what is the speed? That's the question. And what we're going to do is we're going to use the motion diagrams to answer this question. Then we'll be able to do the energy. So let's see what this looks like. The thing that I know for sure is that I'm looking at this, and this is the mass axis here. This top axis is the mass, the vertical, and this one down here is the velocity. So what's it look like? Well, I have a 1/2 kilogram car. Let's say it's that big, and it's moving to the right at 6 meters per second. So the up and down value is the mass. So when I go to do the green car, well, its mass is twice as much, so you can see it's twice as long on that axis. But it's not moving either left or right, so we don't make it into a box because there's no motion. So can we calculate the total motion quantity? Well, the total motion quantity is this area. So the mass is 0.5. The speed is 6 meters per second, 6 times 0.5, so the total area here is 3. What's happening over here? Well, if we say it's just one combined car of a total mass of 1.5, then we see it's this long. But the thing about the motion, and this is what I love about doing our problems like this, is that the motion quantity here has to equal the motion quantity here. There's a big equal sign here. So whatever I have on this side, area of 3, has to be the same area over here. But how tall is this one? This is a total of wrong color. This is a total of 1.5 kilograms. Now, obviously, we saw this demonstration, it totally slows down, so it's going to be less slow, or it should be less fast. So we're trying to find out what is the V here. Well, how are we going to do that? Thing is, I know the area here has to equal the area here. So this total area here has to be 3 because it has to match this area. Area on this side has to equal the area on this side. And if its area is 3 and it's 1.5 tall, how wide does it have to be? 2 meters per second. So we can also think about this conceptually. The initial car was a 1/2 kilogram going at 6. Now it's 1.5 going at 2. 0.5 times 6 is 3. 1.5 times 2 is 3. Or think about it this way. The mass was 0.5. I tripled it to 1.5, which means the speed was 6. And instead of tripling, it went down by a factor of 3 to 2. So now we're able to see how the motion is going to inform our understanding of this. And now what I want to do is I want to calculate the kinetic energies and see how does the energy before compare with the energy after. So let's do that here. If I come over here and I calculate, this guy's not moving, so he doesn't have any kinetic energy, but this guy does. If I go to calculate the kinetic energy, it's 1/2 mv squared. 1/2, we decided the mass was 0.5. The speed is 6. We can probably do this one in our head. 6 squared is 36. Half of that is 18, and half of that is 9. So 9 joules. Well, what's going on over on this side? We have one big blue object here, and so we're going to calculate its kinetic energy. Again, 1/2 mv squared. 1/2. The total mass of this one is 1.5, and its speed turns out to be 2 meters per second. So in order to calculate this, we got to get the speed from the motion diagram down here. 2 squared is 4, half of that is 2. 2 times 1.5 is 3 joules. So I started over here with 9 joules, I ended up over here with 3 joules, which is totally fine, which means I lost a bunch. In fact, if I started with 9 and I lost 3, it looks like I've lost 6. So let's change our diagram so it's a little bit more representative. I'm going to do something fun, and I'm going to make this so it's 9 boxes tall, so each box is 1 joule. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So the total energy is 9 joules here, each box being 1. What do I have over here? I have 1, 2, 3. Where'd all the energy go? Well, it was lost to the surroundings during the collision. How many? Looks like 6. There we go. 6 lost to the surroundings. So here's the full take on this. And the thing that's important is we realize that this motion quantity is always going to be equal to this motion quantity, and it's going to inform our understanding of the energy. So that's all fine and dandy.